So I'm going to just talk about this assignment that I just activated. And so this assignment I just activated for you guys and what you guys need to do for it. And just in general, so this one won't require any new knowledge. This is kind of like the capstone of what you guys need to do. All right. So notice that it's that's a 3-page PDF with 5 sections, and note that the first two sections are noted. Read the links, and did you click on the links, right? Which I'm about to go over here. So your assignment, which will be the last. So now we're now in the point of programming some basic games. So this is going to be what we call a 0-player game called the Game of Life. The Wikipedia article is found on the first link, and this is the Game of Life. We're going to be running it with the whatchamacallit, using ASCII characters. So just an array of characters, right? No problem there. And so let's go ahead and go over what the rules of the Game of Life are. And I've started you off with some skeleton source code that you'll be able to use. The functions that you'll need to complete. Okay, so file. So go back over here. Okay, so let's go ahead and see how the Game of Life works. The Game of Life works. It's a grid simulation, and it works off of some very simple rules, right? And the rules are as follows. Okay, so let's zoom in a bit. All right. So zoom in some more. So the rules are as follows. If a cell, so cells are either alive or dead. In this one, yellow is alive and gray is dead. Okay? So a cell will, and these cells are very fickle. Okay? They represent like little, maybe individual cells and like tiny little cells or maybe little creatures, but they're very, very fickle. Okay? They die because of the most random reason whatsoever. They die if they get too lonely, and they die if they get overcrowded. Okay? So, for instance, if a cell has 8 neighbors, right? The 4 guys who are next to him and his 4 diagonals, right? So if he has less than 2 neighbors, he's too lonely, and he'll die. If he has less than 2 neighbors, he's lonely and he'll die. So less than 2 neighbors, he's lonely and he'll die. Okay? But they can also die of overcrowding if there's too many neighbors, right? If you have, say, more than 3 neighbors, you have a tendency to die. So it'd be from overcrowding. So this guy's got 6 neighbors. He's way overcrowded, so he goes away. And all the cells around him also. And everybody else who had 3 neighbors goes away. These guys only have 1 neighbor each, so they're going to die. And this guy's only got 1 neighbor, so he's going to die. Then there's one other rule. Okay, so that's how cells die. They die if they get too lonely, which is if they have less than 2, I believe. Let's go ahead and see what the common... Let me just make sure that's the rule. For all I keep saying it. Yep. So fewer than 2 neighbors, it dies. If you have 2 or 3 neighbors, you're safe, right? If you have 2 or 3 neighbors, you're safe, right? Because if you have more than 3, you're overcrowded. So more than 3, you die from overcrowding. Less than 2, you die of loneliness. 2 or 3, if the cell has 2 or 3 neighbors, it's safe. So how do we get new cells? Because new cells were popping up when we were doing stuff. Well, the answer is that if you're a dead cell and you have 3 live neighbors, like this guy does, you come to life. Okay? Which makes this very simple pattern over here very easy to understand. So look at this guy. First off, these are static positions, right? Each of these guys has 3 neighbors, so they're all nothing special gonna happen, and all the surrounding cells only have 1 or 2. So this is static. It's not going to change. Likewise, all these cells over here, they only have 2 neighbors, so they're cool. So this guy has 2 neighbors, so obviously he's going to stick around. But his neighbors each have only 1 neighbor, right? Right. This guy has only 1 neighbor, so he's going to die. This guy has only 1 neighbor, so he's going to die. But over here, this point over here, to the top of the center point, he's got 3 live neighbors, so he's going to spring to life. And this guy over here has 3 live neighbors, so he's going to spring to life. So if we click next, notice that it's an oscillating pattern, right? In this configuration, these guys have 3 neighbors, but they have 1, right? So see how these simple rules make it flip back and forth, right? Everybody following me so far? Okay. So all we're doing is simply saying, are you alive or dead? This next step. So one of the more interesting things, though, is that these rules can create very, very complex behaviors, like this glider. So note the cells that are going to die. So note the cells that are going to die. Next, right? So this guy's going to die, but this is going to come to life. This isn't. This isn't. Sorry, this one is. So watch what happens. It's the same 4 patterns repeating over and over again, and each time it repeats, it moves down a little. This is what we call a glider, which is named thus because it glides across the game board. Okay? New developments, playgameoflife.com. Close. Right, so next. So let's go ahead and start this, right? Other things like this exploder, you know, they do exactly what they say on the tin. They produce some interesting behaviors. And eventually they get into like a static space. Right? And this is what we call a Gosper glider gun, which is very interesting. This is basically a factory that somebody figured out how to make that produces a bunch of gliders. So notice the 2 things that are moving back and forth. They collide with each other, turn around. Right? And the only programming that's going on here to figure out like how to produce the gliders is whether or not these cells live or die. There's no like checking for collisions or anything. It's merely, do these cells have the appropriate amount of neighbors, right? So it becomes very, very interesting. Okay, so we're going to make a much easier to, what I care about here is the logic, and we can make a much easier to write version of it. So I've given you a Game of Life board, which is an object that represents the game board for our Game of Life class. All right, so it's not too exciting here. It has a class, and we're going to be using a technique called double buffering, essentially, which means that we have the board, and we're going to use that to generate the next board, okay? And then, so basically it's every time I hit next, we increase the step, right? So we increase a step each time. So essentially we've got a couple functions here that you need to figure out. This is actually going to be the bulk of the work over here. But the idea here is that we're using character arrays to generate our board, right? And the board we draw our characters on the board, we display it to the user, and then we're going to generate the next board, right? And basically, the reason we have a board and a next board is that you can't draw on the board that you're using to generate the next board, because if you draw on that board, you're going to modify the thing you're using to generate the next board. So I have the write-up here, right? And I explain the rules. Each of the status changes happen each step. So if a cell has 5 live neighbors on step n, its status changes to dead for step n+1. So to implement it, we are going to represent the 2D array we're going to use a second 2D array as a buffer, which is a workplace to create the next phase of the game. So here's what you need to implement for this class. You need to implement the constructor. So the constructor builds the initial game of life and however big you want the board to be. And it also initializes the next board so that you have an empty board to work with. Okay, the get neighbor count is the one that I recommend writing once you've after you've created a board, right? Okay, this is very, very important. It's so important that I wrote this in bold for a good reason, and then I wrote it in italics, and I had to bold it over here because this is super, super important for you writing this program successfully. Don't try to do the whole game first. Instead, work on this function, which says given a row and a column, right? Given some row and some column of one of these cells, okay? Return how many neighbors it has, which will be a number between 0 and 8. Now, why do you need to do this one first? Because it's going to be the most challenging method. Why is that? Well, because most cells have 8 neighbors, but not all of them. Some of the cells, they live on the corners or on the sides. So if you try to look if you try to look in the column to the left of the guy on the left side, you're going to get an out of bounds exception because you're looking at index -1, right? So the challenge of this function is that each of your neighboring cells you need to check they could be out of bounds. Okay? So the way I solve this, so there are 2 ways to solve this that I've seen, and I recommend the first one. The first one is to write 8 if statements, right? You basically you start out by saying the number of neighbors I have is equal to 0, okay? And then I have 8 if statements, one for each row, one for the cell in the top left corner, one for the cell above me, one for the cell in the top right corner above me, to my top right. Then directly to the left, directly to the right, and then to my bottom left, then bottom center, then bottom right. Each of those can go out of bounds in a different way. And so basically you check, hey, is this going to go out of bounds? Is it not out of bounds? And is the neighbor there, alive? If so, add 1 to my neighbor count, and that's it. The other way is to use try-catch statements to catch whenever you go out of bounds, which we haven't gone over, but you can look up because I've seen a lot of you trying to use them. So then you do the generate next step, which for each cell on the board, use the neighbors and the state of the and the status of the cell you're currently at to figure out whether the cell is going to be alive or dead next round. You want to change the cells on next board, not your current board, because if you change the cells on board, you're going to lose your current board state, which will make sense as you're working on it. And then the last function is to print out the board, which is fairly easy. The main function is also fairly easy. The only thing that's really hard is the get neighbor count because it can potentially crash. So you need to write it and test it to make sure that it's not going to crash on the corners and the side cases. Right. So